Okay, so this is the new thing, which is, let's see. So in the recent past, I've been working with differential equations of the form y prime is ay, right? And same whiteboard. And I have this kind of statement that if I have a bunch of eigen values, right? I'm going to assume for argument's sake that there are at least two. So if I have some list of eigenvalues and I have associated eigenvectors, and I guess I should put in that these are real eigenvalues. And then if I have kind of associated eigenvectors, right? Then I can write my solution as y is c1 x1 e to the lambda 1 t and c2 x2 e to the lambda 2 t and kind of so forth, right? You guys with me on that one?
Yeah.
Okay, so that's assuming that all the eigenvalues have an eigenvector.
An eigenvalue not have an eigenvector?
Well, there's this behavior that can happen, right, where I have an eigenvalue repeated.
Right.
And sometimes it happens, like in the case of the, in the case of, say, the identity matrix, right? I have lambda 1 is 1, and lambda 2 is also 1. And I can come up with distinct eigenvectors for these. I can say that 1, comma 0, 1. I don't know why I picked that one as my first one. And 1, comma 1, 0. Right?
Yeah.
Are eigenpairs. And the reason that this talk is right now super vague is I don't really have a concept of dimensionality in here because we didn't build very much linear algebra machinery. But suffice it to say that if I have a matrix here, A, that's n by n, if I have n distinct eigenvalues, I'm okay. If I can produce distinct eigenpairs, I'm okay. But it does happen sometimes that I will have an eigenvalue that's repeated, and I won't be able to produce a second eigenvector for it. An example of that case would be something like the matrix 1, 1, 0, 1. In this case, I have lambda is 1 and 1, but I'm only able to produce one eigenvector, or one eigenpair, and that eigenpair is this guy. You guys might remember I started with this as an example. Or something very similar. You guys down with this?
Mm-hmm. Yeah.
Okay. So there's this concept of a generalized eigenvector. And I need a definition for that so I can sort this out. So let me use this kind of second example as a way to figure out what that vector is. So what I'm going to do is I'm going to take that matrix that I'm considering, and I'm going to say I have an eigenvalue, or sorry, an eigenvector, right? If that matrix minus lambda times the identity matrix all times a vector x gives me the 0 vector, right? So this is the usual eigenvector. So my matrix is 0, 1, 0, 0, and then I'm multiplying that by a vector x1, x2 to get the 0 vector. And this is where I kind of notice this guy. You guys with me on that? Yes? No?
Yes.
Okay. So a generalized eigenvector is a vector that gets mapped by this same matrix. So my A minus lambda I matrix. And I'm going to say this is U1 and U2. And this thing gets mapped to the eigenvector. So it doesn't go to 0, it goes to the eigenvector. And then if I hit it with this matrix again, it's going to go to 0. Does that make sense?
Can you just do that?
Okay, so really the kind of an eigenvector, I'm thinking A minus lambda I times x is the 0 vector. And a generalized eigenvector, I'm thinking A minus lambda I times u. It's a shit symbol. Times u is equal to x, where x is this eigenvector. Does that kind of make sense?
Yeah.
Okay, so in this case...
So you're just trying to solve for you on YouTube.
Yep, exactly. So in this case, I get this, I get the equation u2 is 1, right? Which really tells me that any old vector of the form whatever comma 1 works.
Yeah.
And so you can pick whatever you want. I'm going to pick 0. Okay, so now I have a generalized eigenvector. And so I don't quite have an eigenvalue pair, right? So if I was to try to solve this other equation, right? So I'm trying to solve, say, the equation y is 1, 1, 0, 1. Oops, sorry. Y prime, rather, is 1, 1, 0, 1 times y. I know that I should be able to say, all right, y is C1, and then I have a, what's my eigen pair?
1, 0.
Okay, so I should be able to say it's 1, 0, e to the lambda 1 t, right? So this is the part that was usual.
So then you would have C2 times 0, 1, e to the something t.
Okay, and then this is the part that gets a little weird. I have a C2 times, and now I need my generalized eigenvector is 0, 1, and e to the lambda t. Whoever's typing, can you mute your mic?
Sorry.
No worries. So I have a 0, 1 e to the lambda t. So that's my u e to the lambda t part. And then I have plus, and I have my eigenvector, 1, 0, and then a t e to the lambda t. Does this kind of make sense?
Yeah.
It should feel a little bit like the repeated real case for Twackelchodes, right?
Yeah.
Like, oh yeah, I just slap an extra T on there and it's all good. Like, that's the spirit here at least. Except that if you just slap another T on there, it doesn't get you out of the kind of vector space that you were in, right? The subspace that you were in. And so in order to remove yourself from the subspace, you need this this generalized eigenvector that gets you another direction to go in. Does that kind of make sense?
Mm-hmm.
Okay. So that's the general form of these, and that's the kind of content that I want you to have from this section. Do be aware that this is not all the content in this section. So if you're trying to read section 10.5, I'm only talking about the 2x2 case, and I'm only going to assign you problems about the 2x2 case. The 3x3 case is similar, but it's enough more complicated that I don't want to tweak you out. Does that make sense?
Yes. Yeah.
Okay, so I'm gonna. When I was writing this down, I realized too this second part should be. Oops. This second part should have a. It should be the eigenvector times t times e to the lambda t. And now, if you would ask your question again for the fourth different time, if you could use 4 this time, that would be great.
What if it was like lambda was 5? Like, would you have 5t times e to the 5t?
You would have a t times e to the 5t.
Okay. But what if it was 4?
If it was 4, it would also be a t times e to the 5t, because 5 is better than 4. No, it's e to the whatever the eigenvalue is. Yeah, so the eigenvalue only needs to go in the exponent. If you put it down front, it'll only change the constants. It won't do anything else.
Are you gonna post a practice exam?
Yes, and I'll post a practice exam.